These are the attractive handmade shapes in a box, and they're presented in such a way that you can see how one shape is generated from another. All of them come from the basic 5 Platonic solids: the tetrahedron, the cube, the octahedron, the dodecahedron with its 12 faces, and the icosahedron with its 20 faces. But these are presented in what's called the excavated form, and we can see what that means because if we open up this tetrahedron, then we can see inside we've got the excavated form. That's the center of the tetrahedron in there, and it's made of 4 pyramids which have been put together with their vertices at the center. That's how this is formed, and it has various interesting ratios within it. So that's what is meant by excavated. We also need to know some simple language. We need to know that this is called an edge, that's called a face, and this is called a vertex. All of these shapes fit perfectly inside a sphere. So here's an example of that. There's a circumsphere. The vertices all fit on the inside of this sphere. And in point of fact, there's another insphere that touches the centers of these faces. If you can imagine that, there's a sphere inside the insphere as well as the circumsphere. So that's a bit of vocabulary. Now these shapes are related to one another in a special way. For instance, these shapes are said to be duals of one another. If you join the center of the face here to the center of this face here, that is to say, you join that point to that point to that point to that point, making a new shape. And when you look inside, you'll find that what you've actually formed is an octahedron. So this is the dual of that shape. And same again, if you take an octahedron and you mark the centers of each triangular face and you join them all up, then what you find inside is a cube. So this shape is the dual of that one, and this is the dual of this. They're mutually dual. These shapes are also mutually dual, and perhaps you can see that if you join the center of this face to the center of that face and that face and that face, you'll have one vertex with 3 edges running from it. And if you examine the dodecahedron, you can see you've got a vertex with 3 edges running out from it. So these two are also mutually dual. The tetrahedron is special. It's got all sorts of properties. And if we join the centers of the faces of the tetrahedron, then we find we have another tetrahedron inside. So it's begotten another little tetrahedron inside itself. So this is called a self-dual. This is a self-dual shape. So that's how these shapes are related one to the other. And in the excavated form, you can see there's the octahedron and the cube, which are duals of one another. And then we have the dodecahedron and the icosahedron, which are duals of one another. And there's the tetrahedron, which is self-dual. The next method of generating one solid from another is truncation. And truncation means cutting and in this particular context it means cutting an edge in three. So that length there, that edge, has been cut into three equal sections. And you can see that a pyramid is formed at the vertex, if you do the same to each edge, which can be cut off. The pyramid can be sliced off. And what are we left with? We're going to be left with an octagon here on this face. 1, 2, 3, 4, 5, 6, 7, 8. And then if we examine the truncated excavated cube, you can see that you've got an octagon on that face. And as you'd expect, when you've taken off the pyramid at the vertex, you're going to be left with a triangular face. So that's the process of truncation. All of these 5 shapes have their truncations. That's the truncated icosahedron, which is the football shape. This is a truncated dodecahedron. That's the truncated tetrahedron. And this one is the truncated octahedron. This one has a special property that if you look at that central angle, all of these angles at the center of the sharp angles of an isosceles triangle, and it so happens, and it's easy to work this out with some Pythagoras' theorem, that the angle at the center of this particular shape is the sharp angle of the famous 3, 4, 5 triangle. All of these ratios and proportions can be worked out with simple geometry, and they have considerable interest for mathematics and other subjects. So now we've understood how we can form these two, the cube and the octahedron, which are duals, and the dodecahedron and the icosahedron, which are duals. And we've also seen how you can find the truncations of all of these 5 Platonic solids. But that leaves us with one other way of cutting the edges of a shape, and that's cutting the edge length in half. So if you cut this edge length in half, now you can see there's our cube and the edge length has been cut in half. And if you do the same to every edge, you're going to be left with a square in the middle. You'll have a square face there, and when you cut off these pyramids at the corners, then you're going to be having a triangular face there. Now the interesting thing is that whether you take a cube, divide the edges in half and cut off the corners, or whether you take an octahedron, and do the same thing, you are going to find you end up with the same shape, which is this one here, which is called the cube octahedron. So the cube octahedron is a kind of halfway house between the cube and the octahedron. And it's also got a very special property that this is an equilateral triangle in here, and the edge length to the radius is 1 to 1. In the same way, if you cut the edges of a dodecahedron in half and join them accordingly, then you will end up with a icosydodecahedron, which is this shape. So if you halve the edge lengths of that shape or this shape and join them together to form faces and new vertices, you get the icosydodecahedron. And this shape has another very special property, that the ratio of the edge length to the radius is the well-known golden ratio. Now it's a curious fact and something worth thinking about, people who like to reflect, that these two ratios, the 1-to-1 ratio of the cube octahedron and the golden ratio found in the icosahedron, also occur in our very own human form. For instance, if you look at the full width of your arms, that's the same as your height. So you have a ratio of 1-to-1. Of course, at the appropriate level of accuracy for biology, but you have the 1-to-1 ratio in your human form there. And the golden ratio also appears in the human form because the distance from the top of your head to the navel and from your navel to the bottom of your feet is the golden ratio. And then again, the ratio between the distance from your navel to your bottom of your feet is also in the same ratio to your full height. So quite why these very simple ratios turn up in the human form as well as in these very simple shapes in the icosahedron and the cube octahedron is something for scientists to think about and explain. Or so perhaps the professor of the public understanding of science could tell us why the ratios appear in these two places. Thank you for your attention.